All right, don't forget to put your name in chat. Damn it. Tripping over everything. Let's see. Keep my clock up and running. Oh, we're almost at time. Yeah. If you haven't already done so, please make sure your name is in chat. And my cats are going to start fighting. Okay. I hope my little cat doesn't decide she needs to be on my computer keyboard today. Last night I was in a Zoom meeting and she decided that was a perfect time to get in front of me and have me pet her. And then she decided my keyboard was a place to be because it was warm. So she opened up a bunch of windows on there. I don't even know how she got where she got, because things got opened I'd never seen before. Anyway, please make sure you're signed in to the chat. And in just a moment, I shall be sharing my screen. Any questions about anything right now? Okay. If there's no questions or concerns, I'm making the assumption y'all are in MyLab. I haven't dived in there too deeply this week. I'm going to be doing that this weekend or after class today. And looking at where everybody's at. Oh, what the hell? That wasn't supposed to happen. So please be aware that I don't always see when people pose a question in the chat or a comment. So bring it to my attention so I can deal with it. All right. This is the last slide we did in class. And where we put this is the formula for the area of a sector. And a sector is formed by a central angle. And so this would be the sector, and the area would be the radius times the arc length. I mean, times the it's very similar to the area of a circle. I mean, area of a triangle, because it is triangular in shape. So 1/2 times the radius squared times theta. It's very similar to the area of a circle. It's just we have to throw in the 1/2 in there because of 2 pi. And we want to bring it down to the pi angles. Anyway, so that's what we were doing there. And we're going to start with, come on. We're going to start with this. Let me pull up my, oh, that's not what I wanted to do. Let me go back to there. This is what I wanted to do. Okay. See. Okay. Suppose an object moves on a circle. So this is what we're talking about, speed, velocity. So you have something that is being rotated. So it's rotating very fast or very slow, it doesn't matter. So we want to talk about the linear speed. So we're going to talk about this arc length, the arc length. How fast is it going at the end of the arc length if this is s and this is theta, and the object is traveling at in t number of units. So this is t is a measure of time. Measure of time. And s is the arc length. Which is r theta. So we have r here is what s is. And so the velocity, the speed is how far s being divided by how long it took to get there. miles per hour. Okay, drive 65 miles in an hour. That's 65 miles per hour. It was traveling at 25 feet per second. So at the end of 1 second, it's gone 25 feet. So that's what they're talking about here. Okay. Now, angular speed, well, if we're talking about the same thing, we want to know how fast is this angle growing? So how fast does it sweep out that area? So, and for angular speed, we're talking about, we're using the Greek letter omega for that. And so how long does it take this angle to happen? I mean, we have this angle happening divided by in that amount of time. So it swept out a 45-degree angle in 1 second. So that's a pi force per second, pi force radians per second. And we have another way of writing v for the velocity or the speed, because of the relationship between s and theta. We could say theta is the arc length over the radius. So omega can equal s over r being divided by t. If I multiply both sides by the radius, wait a minute, s over t, s is, I'm confusing myself. I always do that with this one. I always end up confusing myself. Okay, I'm going to replace s with r theta. So s equals r theta. Or theta will equal s over r, and I replace theta with s over r over t equals omega, multiply both sides by r, and I get r theta equals s over t, which is the velocity. So the velocity equals the radius times the angular speed.
Can you do that one more time? Can you explain that one more time, please?
Say again?
Can you explain that one more time, please?
Yeah, let me get a different page up. Okay. So S equals r theta, right? The arc length is the radius times the angle measure, and this is in radians. Right? And we have the velocity equals s divided by the amount of time it took. So I can say that I can replace s with r theta, or wait a minute, what did I do? No, I didn't do that there. I did omega is theta over t, right? So that's the angle velocity or the angle speed. So how long did take it to go that angle. Okay, it's similar to arc length. We're covering the same amount of distance, but are we looking at the angle movement, or are we looking at the movement on the arc? So it's just looking at two different things of the same motion. All right. And so I solve for I solve for theta here in this one. So I get theta equals S divided by R. So I can replace, I can take this and put it in for theta here. So now I have omega equals S over R being divided by T, by the time. So if I multiply this side by R, so that means I'm going to multiply the numerator of this fraction by R, and I have to multiply this side by R. So these two R's will go to 1, and so this leaves me R theta equals S over T, and S over T equals the velocity, right? S over T equals the velocity. So that's where they come up with this formula down here, that the velocity can also equal the radius times the angle speed. So the speed on the arc, so we're talking about what happens on this arc can relate to the speed of this angle, of the creation of the angle, or the speed of the creation of the angle is related to the velocity, to the linear speed. So the angular speed is related to the angular speed and the linear speed are related to each other, because you can't have one without the other one. Did I help there? Make it more clear or less muddy? Yeah.
So basically you take, you find theta, you take that, and then you find R, and then you use R to solve for the velocity.
Yeah. Sometimes you're given everything and except for one of the variables, and so you always solve for that one variable. So that's how formulas work. Formulas are about these are known quantities, and you put the known quantities in appropriately to find the missing piece. So whatever is missing. Sometimes you're given R. So if you're given R and you can calculate the angular speed, then you can calculate the linear speed off of the angular speed. Or if you're given the angular speed, the linear speed, V, if you divide that by R, that will give you your angular speed.
Yes, sir.
So as long as you have the radius and you have one of those two speeds, you can find the other one. Because the time here is the same time for both of them. The time for omega is the same time for this for the V. So the only difference here is, do you need R in the computation, or do you need to take R out of the computation? So if it's angular speed, you need to take R out of the computation, and if it's linear speed, you need R in the calculation. So making sense?
Yes, sir.
Okay. Yeah, I need people asking me questions because I understand this better than I used to after today. Now, finding linear speed. So we have we have this circular motion, and this length is 2, and the speed is calculated in revolutions. So it does 180 revolutions per minute. So that's our RPM. Back in the day, records were 33 revolutions per minute, 45 revolutions per minute, 78 revolutions per minute. So that's when they talk about a 45 or 33 and a third revolutions per minute. That's what they mean. The record revolves that many times in 1 minute. And technically, they say that the higher the revolutions, the better the sound quality. I don't know if that's true or not. My ears can't tell the difference. So if you're recording something on tape, if the tape speed is fast, it should pick up more sound than if the tape speed is slow. Anyway, it has nothing to do with what we're doing. So we did 180 revolutions. So what angle are we talking about? Well, that's everything has to be in pi, right? Or actually, let me see here. Let me back up. Does it say? It does not say theta has to be. In radians. Oh, omega is in radians. Okay. So this is 180 times 2 pi per minute. Revolutions. Well, per minute. Because the revolutions, 180 revolutions, one revolution is 2 pi. So we're still per minute. And so this is 360 pi radians per minute. Or now, velocity is arc length per minute. So it's doing 360 pi. Well, oh no. I lost the formula. So S over T, and S is R theta. And so 2 times 2 pi. So now I have to multiply this by 2, because it's 180 times 2 times 2 pi per 1 minute. right? Because this is the arc length or the speed is 2 times 2 pi times 180, which tells us how often it did it in the minute. So that gives us what, 720 pi per minute. What are they asking for? Linear speed. Okay. And so you do 720 times pi, and you punch that in the calculator. Okay. Well, they get omega is how many revolutions per minute. And so 180 revolutions per minute. One revolution is 2 pi. So 2 pi radians per one revolution gives us the 360 pi radians per minute. That's the speed. What was that? Oh, okay. And so that gives us the angle velocity. Yeah, what I calculated here was angle velocity. And so the linear speed of the rock is r times the angular speed, which is what I did. Okay. And then they multiplied it out and rounded to the whole nearest whole number. Questions? You won't have too many questions on this in the homeworks. You'll have one or two. Oh, I totally forgot about this in my first class today. I have posted in the syllabus, and I think I put it in announcements, the exam dates. And they're all on a today's Thursday. They're all on a Thursday. So that means we have a review on the class day before. So that Tuesday, we'll have a review followed by the exam on Thursday. All right. And here's the deal about my exams. If you didn't see it in the homeworks, you won't see it on the review. Well, the material covered. The questions will be a little different. And then if it's not on the review, you won't see it on the exam. So if you can do the homeworks and you don't have big problems with the review, then the exam should be a cakewalk. Right? Easy as pie, falling off a log, all those wonderful euphemisms for saying it's easy. So I'm sounding like my professor in my master's program. It's easy. No, it isn't. It's easy for him. He has a PhD in number theory. Okay. Now, so the linear speed, okay. And they converted that 2,262 feet per minute to the number of miles per hour. How did they do that? Well, how they did it is 1 minute equals 1/60th of an hour. Okay, 1 minute. So we have 1 minute. We have the unit fraction, 1 minute over Oh, no, no. We have 60 minutes is the same as 1 hour, or 1 hour is the same as 60 minutes. Yeah, but since the minutes is in the denominator, so this is, and I would write it this way, per 1 minute. Since I want to get rid of the minutes and I want to put in the hours in the denominator, so I'm going to multiply it by this fraction. So I'm going to take the 720 pi, well, actually, we're going to use the 2,262 divided by feet divided by the 1 minute. I'm putting the units of measure off to the side. So this will be 60 minutes over 1 hour, because now the unit measure goes away and we put the hour in. Okay, and now I want to convert the feet to miles. So that means I want to take out feet and replace it with miles. So I'm going to put 1 mile over 5,280 feet. Did I remember that right? It's been a long time since I used it. 5,280 feet is 1 mile.
Yes, sir, you're correct.
Okay. So I'm going to multiply by this unit fraction. I'm doing a dimensional analysis here. And so I have 1 mile over 5,280 feet. That way the units of feet go away and miles stay. So it's going to be miles per hour. That's the unit is mile, the speed unit is miles per hour now. And all I have to do now is multiply 2262 times 60 and divide it by 5,280, and that'll give me the number of miles per hour. And they rounded it to 1 decimal place, which is 25.7 miles per hour. Yeah, dimensional analysis isn't hard. It's a little tricky, and it's about multiplying by those unit fractions where the numerator and denominator are in different measurements, but they're the same. They measure the same amount of length, the same amount of time. It's just you're using minutes instead of hours, or feet and miles, or feet and mile and yards, or feet and inches. So it all depends upon what you're converting to, and what you want to take out and what you want to put in, and what do you want to replace it with. So here I wanted to take the feet. I want the feet to go away. So the feet was in the numerator, so I needed to divide by feet. So those will go away, and I'm replacing the feet with the mile. So the mile goes in the numerator. And same thing with the hour and minutes. It's just I switched numerator and denominator on us. Okay. We don't do too much of that in this class, but it's a good skill to have. All right. Now comes the fun part. Yeah. Most people cringe when I say fun. All right. We're going to find exact values of trigonometric functions using a point on the unit circle. So a unit circle is a circle that has a radius of 1. And I wasn't able to do that today. Let me see. Which one do I want to pull up? Oh, yeah. Here we have, this is a unit circle. with a bunch of angles shown in it. All right. And this is overlaid on the XY axis. So this, so this is the X axis. And this is the Y axis. And so we have points on the circle. We have this point here, this point here, this point here. These are specific angles, and they're important angles that we use because they're known quantities. And with trig identities and formulas, we can represent most angles by using these basic angles. So if we want to find exact measures, we can do that. Okay. And so find the exact values using a point on the unit circle, finding the exact values of the quadrantial angles. The quadrantial angles are the angles that are on the X and the Y axis. Let me change the thickness of my pen. So we have the portion of the X and Y axis that the radius lands on. So these are the quadrantial angles. Okay. So oh, in files, this should be in files. And there's another one I need to put in files, and I meant to do that before class today, but I was otherwise occupied. And then we have another angle that goes all the way around. So it does one complete circle. And that's what we taught. The quadrantial angles are the angles that land on the X and Y axes. So we have 4 quadrantial angles. All right. Now, and then we're going to find exact values of, well, when we get to that section, we're going to do things a little different than what they do on the in the PowerPoint slides or the textbook. We have the 45-degree angles. Let me see if I can do it this way. Here. Ah, yes, I can. And then I hide all that. All right. It's not gone away. I just hid it. So the 45-degree angles, this is the 45 is half of 90, so it's half that angle. And here's another 45-degree angle. I call these the 45-degree angles. And the values of those angles are the trig function values of those angles are going to be the same except for the sign. Sometimes they're the same, exactly the same. Sometimes they just differ by a sign. One is positive and the other one's negative. It just all depends upon which quadrant you wind up in. And we'll talk about more about that. And then you have the 30-degree angle, which is this one. So this one's 45 and this one's 30. And then this one is 60. And this is 90. So, and this is 0. These are the basic angles that we use to create to talk about our trig functions. All right. and then find exact values for integer multiples of pi over 6 or 30 degrees and 45 degrees and 60 degrees. All right, so this one is the same as pi over 6 radians because it is 1/6 of pi. All the way around would be 12/6. So I only want 1/6 of 2 pi gives me this angle here. Well, 1/6 of 360 no 1/6 of 100 of pi, and 1/6 of 180 is 30. So oops, let me disappear that. So this is, let me, this is 180 over here, which is the same as pi. Pi looks weird. Pi looks weird anyway. All right. And then using calculator to approximate a trig function value. If you punch, as soon as you start punching things into the calculator, chances are you're looking at approximate values. It won't be exact. Okay. There are sometimes it is exact, but a lot of times it is not. And then use circle of radius r to evaluate trig functions. I don't remember doing that in the other class, but maybe we did. All right, unit circle, and I kind of set it up here. One revolution around is 360 degrees. It's also 2 pi, and 0 degrees is 0 radians or 0 pi. All right. And then, next line, a trigonometric function of a real number. Let me add another layer and hide previous layers. All right. Let t be a real number and p equal xy. So I have some point here, p on the unit circle, and it's x and y, and it has x and y coordinates. All right. So we have some number t, which is some real number, and the sine of t will equal the y value from this point. So we have this. And that's some angle t. All right. And the cosine of t is going to equal the x value of this point. In terms of the unit circle, that's how cosine and sine are defined. The way you learned about it in geometry, we'll use that as well, but not right now. Tangent is if you remember from, I think, algebra 2 and geometry, is sine over cosine, which is y over x. So our tangent of t is going to equal y over x. So if I know this point, I can find these three trig functions. Now we have another set of trig functions. I don't know if you had been introduced to them before, and they're called cosecant and secant and cotangent. So we have sine and cotangent and cosecant are related to each other because cosecant, and it's abbreviated CSC of t, is going to be 1 over y. The cosecant and sine are reciprocals of each other. That means that if I do 1 over sine, I will get cosecant. And 1 over, since sine is y, cosecant is 1 over y. Secant is the reciprocal of cosine. So secant is written as SEC, which is 1 over cosine. And cosine is x. So that's going to be 1 over x. So we have secant down here equals 1 over x. And cotangent, yeah, is the reciprocal of tangent. And it is written as COT, but it's pronounced cotangent. And so that's going to be the reciprocal of tangent, which is y over x, and the reciprocal of y over x is x over y. You just flip the fraction. So this is x over y. So I'm going to go ahead and write that over here, that sine, written as sine of t, equals y. Cosine, which is written as cosine t, equals x. And tangent, which is written as tan of t, is y over x. All right. So if you're given specific, you need to clean this up a little bit. Okay, and I'm going to add another layer. Now, now we can use point values to determine these trig functions, and that's what they're asking for. Oh, okay, and secant and cotangent. All right. So here we have this point, and this point happens to be right here. Okay, right here. So this is the point -1/2, comma, square root of 3 over 2. And you're asked to find the 6 trig functions for this point. And actually that would be for this angle, because that is what the t value represents, is that angle. And so the sine, let me use smaller. So the sign of this t equals the y value, which is the square root of 3 over 2. The cosine of t is the x value of this point, which is a negative 1/2. And the tangent of t is the y over cosine. I mean y over x, which is the sine over cosine. So I have the square root of 3 divided by 2 being divided by a negative 1 over 2. Now, there's a couple of ways to solve this particular. When you have a fraction divided by a fraction, is the same thing as the fraction in the numerator being multiplied by the reciprocal of the number in the denominator. So the 2's go to 1, and you're left with the negative square root of 3. Another way of looking at this is to say that this is 1/2 times the square root of 3 being divided by 1/2 times a negative 1. So now I have a 1/2 over a 1/2, which is 1. So that just leaves me the square root of 3 over the negative 1, which is negative square roots of 3. Either way, have I said today that I play with numbers? Well, I do. Okay. So we had two different ways of getting the negative square root of 3. Now, all these other numbers, the cosecant of t is going to be 1 over y. So it's 1 over the square root of 3 over 2, which is just the reciprocal of that fraction, which is 2 divided by the square root of 3. Now, in mathematics, for the most part, if you have a square root in the denominator, we want to rationalize it. We want to get rid of that radical down there. So I'm going to multiply the square root of 3 by something so it becomes a rational number. This is called rationalizing the denominator. So it becomes a whole number or an integer number. And so if I multiply the square root of 3 by itself, guess what? I get 3. So the denominator becomes 3. But if I multiply the denominator by a number, what do I have to do to the numerator? This is 5th or 6th grade mathematics. Don't I have to multiply by the square root of 3 again? So I'm multiplying by 1. So I'm not changing how much it is. I'm just changing what it looks like. So my numerator is 2 square roots of 3. So the cosecant here equals 2 square roots of 3. Well, that's just getting weird on me. 2 square roots of 3 divided by 3. I forgot the t. The cosecant of t. And a lot of times I'll put the t or whatever I'm taking the function on inside parentheses, so it's very clear about what's happening there. And now we want to find the secant of t. Well, the secant of t is the reciprocal of 1/2. I mean, yeah, negative 1/2. Or it's going to be a negative, 1 divided by a negative 1/2, which is just a negative 2 over 1, which is negative 2. So the secant of t is now a -2. Okay. And we can look at cotangent in two different ways. We can look at cotangent as being x over y, or we can look at cotangent as being 1 over tangent. That means we take the reciprocal of the tangent, which in this case is 1 over the negative square root of 3, which gives, and then I multiply numerator and denominator by the square root of 3. And so, it's going to be negative, and so that's going to be the square root of 3 over 3. Or I can go this pathway, and x is a -1/2, and the denominator is the square root of square root of 3 over 2. So this becomes a -1/2 times 2 over the square root of 3, and the 2's go to 1. And so this is the negative of 1 over the square root of 3, which is just this right down here, which rationalizes to that. So my cotangent of t equals the negative square root of 3 over 2. Over 3, sorry. And the textbook shows you this without showing you any of the calculations. And so the sine, the cosine, and the tangent were pretty straightforward. They set up the fractions like on tangent, but didn't show the computations they did to get the negative square root of 3. I will show you the computations because it's easier to understand what's going on there. And the cosecant is 1 over the y. And then again, they condensed it down. They didn't show all the steps here. And secant, same thing, only secant was easy because it's just the reciprocal of -1/2, which is -2. And then the cotangent, they did it the x over y, and they still got the negative square root of 3 over 3. Okay, now in mathematics, and especially in trig, we don't use t. We're going to say t is going to be represented by the Greek letter theta. So instead of saying sine of t, now it's sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. And in this case, this particular angle here is, what is that? That's 120 degrees, and in radians, that is 2/3 pi. And we'll look at that more closely in a moment. And here are the quadrantial angles, which I had described earlier. So I'm going to add another layer. And darken the previous layers. So the quadrantial angles, I think I already did this, right? Where we talk about this angle here. This is 0 degrees or zero pi, 0 radians. This angle here, this angle is a 90-degree angle, which is pi over 2. That's a quadrantial angle. Quadrantial angles are angles where their terminating side winds up on a axis, one of the axes. Okay. So 0 degrees is on the x-axis. That's why it's quadrantial. And then we have this angle, half a circle. That's 180 degrees or pi radians. That's a quadrantial angle. And then we have this angle down here. We've gone 3/4 of the way around, and 3/4 of 360 happens to be 270 degrees, or 3 pi halves. I've gone pi and then I've gone half again. And then full circle, they don't talk about the full circle, but I do. You make one full revolution, well, that's 360 degrees. And by definition, that is 2 pi. All right. Now, with the quadrantial angles, we have these 4 points that are associated with the quadrantial angles when it's on the unit circle. Okay. Well, with others as well, but something else comes into play. So, oops, here, let me do something now. No, I'll stay on this one. So the radius, what's the radius? It's a unit circle. It's called a unit circle because the radius equals what? You can say it, you can type it, you can show. Yeah, the radius is 1. Forgot the equal sign. The radius is 1. So if this length here is 1, what's the x value here at this point? So I can talk about the x value.
Equals 2.
The radius is 1.
You said, would you say at that value, at the 360 value?
Right. Or the 0.
So if it makes a full revolution, doesn't it make the
No, it's not about the revolution. What? And now I'm just looking at the coordinates.
Oh, you're just looking, okay. Okay.
Yeah.
Oh,
yeah. This is just 1, right? Because it's 1 unit away from 0. What's the y value of this point? It's on the x-axis. So what's the y value?
0.
0. Now we come up to 90 degrees. and we can talk about the X and Y value of this point. So how far away is this point away from the origin? So what's the X and Y value?
X is 0, Y is 1.
Exactly. Yeah, the fact that it's a circle is confusing some people, but we're just looking at the coordinates now. We know this distance is 1. So this is in the Y direction. It went 1 unit up, and the X value on this line is 0. So we're going to stay for this quadrantial angle. We're staying on the X-axis, so the Y value stays 0. So this point, the Y value is 0, but what's the X value?
-1.
-1. I know it's 1 unit away from the origin, but it went in the negative direction as far as X is concerned. And so this point down here at 270 degrees, we have a similar situation as what happened up here at pi over 2 or 90 degrees, except what happens to the Y value when you're going down?
They become negative.
Negative. So now this point, the Y value is a -1, and the X value is still 0, because all the X values on the Y axis are 0. So now I can find the trig functions on each of these points, because I know what that ordered pair is for each of those points. At 90 degrees, okay? The sine of 90, or the sine of pi over 2, is 1. The cosine of 90, or pi over 2, is 0. And the tangent of 90 degrees, or pi over 2, is X over Y, 1 over 0. What's 1 over 0? What happens when you divide by 0? Do we get a number?
Is it undefined?
Undefined. Thank you. Or UNDF. Now, cosecant, oops. The cosecant of 90, or pi over 2, is 1 over the Y value. Well, 1 over 1, what is 1 over 1? That's easy.
1.
And then secant, the secant of 90, or pi over 2, is 1 over the X value, or 1 over the cosine value. What's 1 over 0? We already discussed that, didn't we? Again, it's undefined. And for cotangent, I'll write it here. The cotangent of 90, or pi over 2, well, that's the X value over the Y value, 0 over 1. What's 0 over 1? This is different than dividing by 0. You're dividing into 0. What is it?
1.
0.
It's 0. This is like multiplying 0 times 1 over 1. So I get 0 because I'm multiplying. If it's in the numerator, you're multiplying by it. If it's in the denominator, you're dividing by it. So here I'm multiplying by 0. Multiplying 0 gives you 0. The only exception to this rule is 0 over 0, which is a different kind of undefined. Oh, so this is 0. And that's how you find all of these. And you're going to get the same number showing up. You're going to have two of them that are going to say undefined because two of them you're dividing by 0. And the other ones are either going to be 0 or -1 because of the -1 there. Same thing is true with the 0, -1. Same thing is true here with the 1, 0 at 0 degrees or 360 degrees. So I'm going to go through their stuff. All right, and I started at 90 degrees. They started at 0 degrees. Okay, so where X is 1 and Y is 0, so sine of 0 is the Y value, which is 0. Cosine of 0 is the X value, which is 1. Tangent is Y over X, so that's 0 over 1, which is 0. And secant is 1 over X, and X is 1, so it's 1 over 1, which is 1. And the secant and cotangent, because we're end up dividing by 0, is undefined. Or not, they say not defined. All right, 90 it's the same thing I had, so I'm not going to spend too much time on it. The difference between the way I wrote it down and the way they write it down is they talk about tangent and secant being not defined. So the ones that aren't defined, they separate them out, which is fine. You can do that. And then the point on the unit circle that corresponds to 180 over here. So sine is going to be 0. Cosine is going to be -1, and tangent is going to be 0 over -1 or 0. All right. Cosecant is going to be 1 over 0, so that's going to be undefined. And then cosecant is 1 over -1, which is -1. And then cotangent, you end up dividing by 0, so it also is undefined. Or so secant and cotangent in this case are not defined, or they're undefined. And for 270, it's the same thing, except it's going to be you're going to get the same values as you did up here with 90 degrees, but instead of being +1, it's going to be -1. So sine will be -1, cosine will be 0. Tangent will be undefined. Cosecant will be -1, and secant will be undefined, and cotangent will be 0. Okay. The quadrantial angles are easy. Yeah, I know some of y'all are thinking, yeah, right. But actually they are compared to some of this other stuff we're going to be doing. All right. And here's a table that shows those. And did I post the? No, I didn't. Well, maybe I did. I have to go back and double check. I created the PDF file that has all these slides on it. I just don't know if I posted it in files yet, and I need to go do that.
I don't think you have.
I did?
haven't seen it in there.
Let me see. Let me look real quick. Let's see. Oh, something's not letting me see. that needs to go away. And it's right behind this. I can't see it because it's behind something that's showing up because of Zoom. So anyway, I'm not gonna worry about it right now. Okay. All right, so to find the exact value here, I'm gonna create another layer. The limit of 5 layers has been reached. Oh no. So I'm gonna go back to this. Whoops. But what if I go that way? All right, there we go. Why? Okay. It's not doing it. It's going to make me, all right. So I'm going to delete everything on this. Well, let me do it this way then. Delete that. Okay. Put add layer. Oh no, here we go. Nope, it won't let me do that. It won't let me just see the basic layer. So I always have to add a layer. All right. I've had this thing almost a year or just over a year. And I'm still learning new things about it, and I keep updating it. So I even have newer things to find out about it. Okay, so 3 pi, which is greater than 2 pi. So that means I went around the circle once. So if I add pi to 2 pi, that will give me the 3 pi. So that means I come over here to 180. And I know this point here is -10. So now I have the sine of 3 pi is going to be 0 because it's the y value. Now, here we have -270. So instead of going in the positive direction, I'm going to go in the negative direction. And I wind up here. Again, it's another quadrantial angle. And so, and I know the coordinates of this point, the coordinates of this point are 0, 1. And I know cosine is the x value. So the cosine of a -270 degrees is 0. So if you know which quadrantial angle they're talking about, it's quite easy to find those. If you know these special angles, you can find out what these points are. And then they kind of repeat over here and according, and then by symmetry rules and other factors going on, you can find out what these are just by changing signs. Okay. All right. And so, yeah, it goes one around and it still winds up at, yeah, the 3 pi. Sine of 3 pi is the same as the sine of pi. So if the angle is greater than 2 pi or greater than 360, then you have a reference angle which is less than 2 pi or less than 360, which has the same terminal side. So the cosine of 270 is the same as the cosine of 90 because they have the same terminal side. The direction of the angle does not affect the sign of your function. Well, what affects the sign of your result is what quadrant did you wind up in. If I wind up in the second quadrant, my cosines will be negative and my sines will be positive. If it winds up in the third quadrant, both cosine and sine are negative. And if it winds up in the third quadrant, my cosine is positive, but my sine is negative. Okay. And that relates directly to the coordinate plane because of how we construct this thing. First quadrant, they're both positive. Second quadrant, the x is negative. The third quadrant, they're both negative, and then the fourth quadrant, the y is negative. And we usually think of positive. So here we have sine and cosine are positive in this quadrant, and sine is positive in this quadrant. All the other trig functions will be negative, except for sine and cosecant. And down here, they're all going to be negative, except for cosine, cotangent and tangent, because you're dividing x and y, and negative over negative is going to be positive. And over here, all the y values, all the x values will be positive. So the cosine will be positive and the secant will be positive, and all the other measures will be negative. So it's just a matter of knowing what's going on there. So here, cosine is positive, and over here, tangent is positive. One tangent's positive up here also. So knowing this fact, well, just knowing that where cosine is, where x and y are positive and negative, just helps you determine these signs here on your functions. Okay. All right. So now we're going to look at this a little differently. And how I'm going to do that is I'm going to drop out of that one. And I have another file that I haven't put into, I have not put into that's a mess, isn't it? I do my best. I haven't put it into files yet. And so right now I'm going to do a layer. I knew it had layers, but I'd never used them before. So I need to add a layer. Okay. No. I want to be on layer 1. Okay. So and you'll get one of these, and this is going to be something you're gonna want to use. And so I'm gonna put it into the files for this class, so y'all will have this for you to use. And so we already determined that this is 90 degrees, which is pi over 2, and this is 180 degrees, which is pi, and this one is 270 degrees, which is 3 pi halves, and this one is 0 degrees or 360 degrees, which is 0 radians or 2 pi radians. And our coordinates here are 1, 0, 0, 1, -1, 0, and 0, -1. We already did those. Now 45 or pi over 2, pi over 4 is half of 90, or half of pi over 2. Pi over 2, you take half of that, that means you're multiplying by 1/2, and you get pi over 4. So that's halfway between here and up here. So that's this angle here. And so this is our 45-degree angle, which is pi over 4. Now to find that, all right, here we have this side here, which are x and y here. Here's the x value, and then here's the y value. So you have x over here and y over here, and this forms a nice 90-degree angle. And if this is 45 degrees, that means this one up here also has to be 45 degrees. So now I have a 45 right triangle, which is an isosceles right triangle. I know the hypotenuse is 1 because that's the radius, and this side is x and this side is y, and I know x and y are the same formula, so I can use the Pythagorean theorem here to find out what x and y are. So I have x squared plus y squared equals the hypotenuse squared. Well, 1 squared is just 1. And I know x and y are the same number, so I can say x squared plus x squared equals 1, because I just replaced the y with x. And now I have 2x squared equals 1, or x squared equals 1/2. Now, when I take the square root, normally in this types of situations, when we take the square root, we have a positive value and a negative value. Well, since I know x needs to be positive, because that's what the picture is telling me, is that x here is going to be positive. So I will only want the positive square root of 1/2. Well, I want to simplify this. I want to rationalize my denominator, so I don't have, because the square root of 1/2 is the square root of 1 divided by the square root of 2, which is just 1 over the square root of 2. Well, rationalizing my denominator means I multiply the numerator and denominator by the same number, so that my denominator no longer has a radical. That's what we mean by rationalizing. It becomes a rational number. It's not an irrational number. Square root of 2 is irrational. You can't reason with it. So I'm going to multiply this by the square root of 2. What happens when you multiply the square root of 2 by itself?
Equals 2.
is 2, because that's the definition of the square root of 2. It's that number you multiply by itself to equal 2. So we get 2 here. And so in the numerator, it's just 1 times the square root of 2. So we have that in the numerator. So that's what the x value is. The x value is the square root of 2 over 2. Well, I know the y value and the x value are the same thing. So that means the y value is the square root of 2 over 2. So this point here is the square root of 2 over 2. And this one is the square root of 2 over 2. So you have the square root of 2 over 2, comma, square root of 2 over 2. And then you just build the 6 trig functions based on that. Cosine and sine of 45 degrees are both going to be the square root of 2 over 2 because they equal each other. And the tangent, you're going to have the same number over itself. So the tangent of 45 degrees or 4 pi over 4 is just 1. Square root of 2 over 2 divided by the square root of 2 over 2. And cosecant and secant are going to be the same number. So I only need to find one of them, and the other one's going to be the same number. And cotangent is the reciprocal of tangent. Tangent's 1, so the reciprocal of 1 is 1. It's the only number that its own reciprocal. Well, 1 and negative 1. They're their own reciprocal. Okay. Because when you multiply them together, you get 1. Okay. So I want the reciprocal of the square root of 2 over 2, which is 2 over the square root of 2. And then I multiply numerator and denominator by the square root of 2. So I get 2 square root of 2 over 2, which is the square root of 2. So secant and cosecant are the square root of 2. Yeah, I went through that kind of fast, didn't I? Because I'm going to show you another way of finding those numbers. But let's look at what they did, okay? And they did the same thing I did here to create it. Please notice that they put the restriction that both x and y are positive. So that's why they just looked at the positive square root. They didn't show all the goings on that I did over here, okay? And so we have sine, we have cosecant, and then we have cosine, and then we have cosecant, and then we have tangent, and then we had cotangent. Well, I know these angle degree. I know that. All right, so let me just create another layer just so I can work these out. All right, I know the cosine by the work I just did. The cosine of 45 degrees is the square root of 2 over 2. And from previous work, the sine at 270 degrees, well, that's the y value of this point, which is -1. And I just multiply the two together. So that gives me the negative of the square root of 2 over 2. And cotangent of pi over 4, well, we had worked that out earlier that equals 1, right? Cotangent is x over y, and x and y are the same value at 45 or pi over 4, so that's 1. And the cosine of 3 pi over 2, again, that's 270 degrees down here. Well, the cosine is 0. So I have 1 minus 0, which is 1. And we already found out that the cosecant of pi over 4 is the square root of 2. Okay. And we're going to square the square root of 2. All right. And the secant of pi, well, pi is over here. Yeah, pi is over here, 0, -1, 0. And so we're going to be subtracting a -1 because secant is 1 over -1. Well, this gives me 2 plus 1 minus the negative is plus. All right. And 2 plus 1 is 3. This is true for very large values of 1. Okay. Now they're going to talk about, and so this is where I change tactics. And I'm gonna pull up a different one. Let me see, do I have it in here? Yes, I do. So this is, I know I put this in the files, and the second page of this has this. And we're gonna build up all the degrees and all the radians, and then we're gonna write down what those coordinates are for each of those points on the unit circle. All right, we have 0. Whoa. Well, I want to see something here. Oh, cool. Okay. So we have 0 degrees, which is 0 radians, and we already determined the coordinates are 1, 0. And then we have 30 degrees, and I'll build the radians up later. And then we have 45 degrees, and then we have 60 degrees, and then we have 90 degrees, which is pi over 2, which is 0, 1. The ones I know I'm going to build across, and those are the quadrantial, and those are outside of a pattern I'm going to show. And then we have add 30 to 90. So I'm gonna take each of these angles here, measures here, 30, 45, and 60, and I'm going to add them to 90 to find the next 3 values. So 30 plus 90 is 120 degrees. 45 plus 90 is 135 degrees. That's one of our 40. We have 45-degree angles that we talk about. And then I'm going to add 60 to 90, which is 150 degrees. And then we have the next quadrantial angle, which is 180 degrees. And now I'm going to go back to the 30, 45, and 60 and add them to 80 to get the next 3 angles. So that's going to be 30 plus 180 is 210 degrees. 45 plus 180 is 225 degrees. So I wrote 220. I don't know why. 220. I can't get it in there right. Okay. 225 degrees, which is 15 squared. Knowing your first 16 perfect squares is essential to know for your math classes. And then 60 plus 180 is 240 degrees. And then the next quadrantial angle is 270 degrees. And then again, I'm going to add 30, 45, and 60 to 270. So 30, adding 30, I get 300 degrees. Adding 45, I get 315 degrees. Adding 60, I get 330 degrees. And then And then the next quadrantial angle is 360 degrees. Oh, I didn't go through here. 90 degrees was pi, 180 degrees was pi, and the coordinates there was -1, 0. 270 was 3 pi over 2, and the coordinates there were 0, -1. And then 360 was 2 pi, because that's one full circle. And the coordinates there again brings us back full circle to 0, 1. Now, what I'm going to do next is build up the coordinates. And then I'll look at let me look at the radians now. The 45-degree angles, which is 45, 135, 225, and 315. They're a fourth. So they're the fourths. We have 1/4 here, so that's pi over 4. 90 is 2/4. So 135 is 3/4. So that's 3 pi over 4. This one is 4/4, and the next one is 5/4. So we have 5 pi over 4, and this and 270 is 6/4, because that simplifies to 3/2. And so the next one is going to be 7/4, 7 pi over 4. So there I built up all my 45-degree angles, and I have 1, 2, 3, 4 of them. That means the X and Y values are going to be the same, or they're going to be opposites. One's negative and the other's positive, or they're both positive, or they're both negative. Okay. Now, 30 degrees.
Professor, just a heads up, it's minute 40.
Okay. Damn it. I wanted to get this done today. Okay. So this is where I'm going to start next time. Okay. This is where I'll start next time, because this is important. This is how we build up these. And once we build up these, it's easy to find the sine, cosine, tangent, and cotangent, and cosecant, and secant. Because once I have the X and Y, it's just, if it's sine or cosine or secant or cosecant, then it's either X or Y, or 1 over X or 1 over Y. And if it's tangent, cotangent, then it's either X over Y or Y over X. And then we just need to say which quadrant is it in, and that'll determine if it's going to be negative or positive. So we'll look at this more closely next time, because this takes about 20 minutes to a half hour to do it right. Okay. All right. So I'm done with you. Unless you have questions about anything, go ahead and ask questions now. If you want to hang around to hear the questions and answers, go ahead and hang around.
Where did you say we're gonna post the file with all the slides?
Post what?
Where did you say you were gonna post the file with all the slides?
Oh, in files. Let me see. Did I put it in there already? Handouts and stuff. Let's see. No, all I've got is the unit circle in there so far. 2 unit circles, and there's going to be a third one. And the third one is the PDF file I was just working off of.
Okay.
It'll have the unit circle with the ordered pairs all the way around, and spaces for the angles. On the next test, on the first test, that you will have to fill that out for me on the test. So, what else? What next? Yeah, let me see if I can do that right now. Because I want to see where that is. No, that's not it. That's not it. Let me go ahead and go there and wait a second. Do I have it? See. I think this is the right file. I'm gonna open it up first before I post it. Because I want to make sure I'm putting the right one in there. Nope, this isn't the right one. This one has one slide per. So that would be like 747 slide, 7 pages. We don't want that, do we? Where am I? There we go. So, whoops. I went to the wrong folder. Is it this one? There it is. Okay. So that's one I'm going to post. All right. And anybody else have another question or anything? Or are you just waiting for me to finish doing what I'm doing?
Nothing else, Professor. You have a good one.
You too. Enjoy your weekend. Come back in one piece, please. Okay. Under handouts,
sir.
it's in there now. Yes, ma'am.
Hi. No, I just wanted to let you know I'm here. I was late because I had an appointment earlier this morning and it ran longer past
That-
11. So
That's
yeah,
fine as long as you
in.
put your name in the chat. I'm good to go. I don't count tardies.
Okay, I'll go ahead and put it in right now, but thank you.
Okay. And the video for this, hopefully I will have time to get it done today. Put it
Okay.
into YouTube today.
Okay, I'll check for it later today or tomorrow.
Okay.
All right, thank you. Have a good day.
You too. Take care. Okay. Oh, and I need to put the unit circle in there. Is that the right one? I think this is the one.
Okay, it's in the files now.
And then the blank sheet of the one that has the ordered pairs all the way around and then slots for the angle measures. I put that one in just now.
Let me reload.
So you
it.
may have to refresh or you back out and come back in. So there should be 3 unit circle documents and 1 PowerPoint document.
So it's only showing me 2. It says 4 handouts and stuff, but it's only showing me 2. The unit circle PDF.
Well, go
And another
here.
one
Let me show you. Let me show you
Okay.
real quick.
Oh, it just loaded in.
Okay. Yeah, it takes a little bit to reload. If you hit if you had hit refresh or F5, it would refresh the screen, and so it would show the current files in there that
Yeah,
got updated. Yeah.
Yeah, I was hitting the refresh, but it wasn't coming in. It just came in.
Oh,
It-
okay.
The blank unit circle chart, correct?
Well, it like over here, you could back out to here and then click back in, and that would have showed it.
Yeah, that's what I was doing.
Oh, okay. It just took it a while for it to pop up on your end.
Yeah, a little
That's
bit
all.
delay.
Okay. Well, such is life, right?
Such it is. All right, thank you.
All right. You take care. We'll see you
I'll s-
next week.
See you next week.
Stay safe. Stay warm.
I'll try my best to.
Okay. Bye-bye. Whoops, wrong button.